I'm just going to work through question 3 from your questions on nuclear reactions. These are nuclear equations. So question 3, I'll just read the question. A radium-224 nucleus decays by emitting an alpha particle and a gamma radiation. So the first thing is write a balanced nuclear particle equation for the emission of an alpha particle from a radium-224 nucleus. So you get most of the information from the table of atomic particles, which is just 2 pages before this question in your booklet. So this is how I know, even though they've just said radium-224, that is the mass number. And so from my table, I found out that the atomic number for radium is 84. And this is how you write radium-224. And emits, so for emits, you draw this arrow to say it gives out. And this is your alpha particle. And then I don't know what this is, but what I did was 224 minus 4, I get 220. And then 88 minus 2, I get 86, because 86 plus 2 should give me 88, and 220 plus 4 should give me 224. And then I looked up element number 86, and that was radon. And question B says, what is the daughter nucleus? So whatever is formed, that's called the daughter nucleus. This is your parent. So the daughter nucleus is radon. Okay, even though you've written it here, you actually have to say what it is. Then the last one is calculate the energy released during the reaction. So for this, if you look up your table of atomic particles, the very last column says nuclear mass. This is the rest mass, and so these, each of them, and it's all to the power of 10 to the power of negative 27. So if I look horizontally along the line for radium, now radium is called the reactant, and these two are the products. So how do you find the energy released? First, look for the total mass of reactants. There's only one reactant here, so the mass of radium, so you have to put in all the significant figures, whatever is given, so no shortcuts here. So 372.057, and then the 10 to the power of negative 27 I get from the top of my table, so I have to put that as well over here. Now there are two products, so it's the mass of alpha particle plus the mass of radon. So I've just put, this is the mass of an alpha particle, you find that at the top of the table, He, it's a helium nucleus, and this is the mass of radon, and they're both times 10 to the power of negative 27, so I've just put them in brackets, and when I add these two, I get 372.0691, and then I just added times 10 to the power of negative 27. So in my calculator at this stage, I'm only putting those numbers in my calculator to get this, and then I just add on the negative 10 to the power of negative 27. Now mass defect is the difference between this mass and this mass. So the difference is the mass of the reactant minus mass of the product. So I just put these two numbers in my calculator, and I just put times 10 to the power of negative 27 outside, and what my calculator told me was 0.04009, and then I just added times 10 to the power of negative 27. So that's your mass defect, or the difference in mass of the products and reactants. And then in order to find the energy that is released, because the products have got less energy, that means energy has been less mass, that means energy has been released. So it's E equals mc squared, where m is the mass defect. So that's your mass defect, and c is the speed of light, and most people write the square here, but they forget to put that in your calculator. So what I've done in my calculator, and I'll just say it, I put 0.04009 exponent negative 27 times, now I know 3 squared is 9, so I just go times 9, and then I did exponent 16. The reason why I did 16 is 10 to the power of 8 squared is 10 to the power of 16. So on my calculator, this is what I put on my calculator. Exponent negative 27 times 9 exponent 16. That's what I got on my calculator. Okay, and then you end up with this answer, and that's the answer in joules, and that is how you calculate the energy released. And I will